Okay, morning. So we'll start with Matthew Penny from LSU, who will tell us about microlensing, another technique whose time is coming, whose time to really shine. If you have questions and you are online, please go to the Wednesday Talks channel and type them in. I will keep an eye on them and try to ask some of them for you at the end of the talk. So please, go ahead.
Thanks. So yeah, that seems like a good place to hold the mic. So yeah, thank you for the invite to come and talk to you. I'm going to talk to you about doing cold exoplanet demographics with microlensing. And to set the scene, this is a plot that has been shown already from Zhu and Dong, showing it's now approaching 5 years out of date, but showing the discovery space of exoplanets, with the majority found to date being from Kepler and transiting surveys, but with growing numbers coming from radial velocities and a few from imaging, and also a growing number now coming from microlensing surveys. But the thing that I want to point out on this plot is the solar system planets. Nearly all of them would not have been found by the present day surveys for exoplanets. So to emphasize the point that Josh made yesterday, if everything was like the solar system, we would have spent 25 years not coming up with much with our planet surveys. But thankfully, there's a wide variety of exoplanets that are different from the solar system, and we have lots to study. But we still want to get into this area of cold, distant planets, and extend that sensitivity down into lower mass areas. There's theoretical motivations for this instead of just kind of wanting to fill out this plot. The region from about kind of 2 to 3 AU is expected to be where the water ice line is. So this is where the region in the protoplanetary disk where water vapor can sublimate, if that's the right direction, into ice particles, and that gives you a big enhancement in the solid surface density of these disks, which is thought to promote the rate of formation of giant planets. So we expect to potentially see large numbers of giant planets at this distance, and the radial velocity and microlensing surveys do seem to agree with this, but we'd also like to know what happens for the smaller planets as well that are stuck in those regions with the giants. Do they survive in systems where giant planets don't form, for example? Okay, so that's the motivation. Let's lay out the. Okay, thank you. Yeah, let's lay out the outline of the talk. So I'll go over an introduction to microlensing first, for those that aren't familiar, starting with the simple case of a point mass lens. Then I'll move on to planetary microlensing by introducing an extra mass into the system, and then talk about how we can use this to learn about cold exoplanet demographics, including how to do it and some of the results so far. I'll then address one of the main limitations of microlensing, which is measuring masses and how we can get around that, before, if I have time, discussing free-floating planets and what is coming in the future. Should use my clicker. I now can't advance, and I can't see the mouse on the screen. Where do I need to go? There we go. Yeah, I can live with that mouse pointer there. Okay, so the introduction to microlensing. So I'm guessing most of you are familiar with the possibility of light being bent by a massive object. Basically, if you from general relativity, mass will warp space-time, and then light traveling through that space-time will travel along a curved path in the presence of that mass. So that's the physics that we're going to be using. And this is the kind of geometry of the system that we're setting up. So we're here on Earth, the observer. and we're going to be observing a bright star at some large distance. And then in between us and that star, there's another massive object going to pass between us with a very small separation or projected separation on the sky from the source that we're observing. We may see this intervening star, or it may be too faint to see. If you have a perfect alignment between the massive object and the background source, then you get an Einstein ring, which is when light travels from the source, it passes by the massive object, gets bent around it and back towards the Earth. And if that's perfectly aligned, you have a circularly symmetric system, so you can form an image at kind of every point along a circle around the massive object. If the alignment isn't perfect, then the symmetry gets broken, and instead of a ring, you get two separate images, one called a major image and one called a minor image. So just to set the scales of this system, what we observe is the images appear to be offset from where the actual source position is. So they'll be offset by some angle. And that angle is usually written in terms of, or characterized in terms of the angular Einstein ring, so how big that Einstein ring would be if it was visible. And we can compute that with, that depends on a few properties. So it depends on the mass of the lens and the relative parallax between the lens and the source star. And this seems like a complicated thing, but it's just a difference in parallax between the lens and the source. So if you're familiar with parallaxes by now, which I hope you are with Gaia, it's just the difference of those two parallaxes. So the angular Einstein ring depends on the mass and the distance of distances of the lens and the source. The typical value for that Einstein ring for a stellar mass object, so kind of a solar mass, is in the order of milliarc seconds. I should say I'm using I haven't written units on these equations. The units I'm using are solar masses, kiloparsecs, because we're going to be looking towards the center of the galaxy at 8 kiloparsecs, and then milliarc seconds are the typical angular unit. So the angular Einstein ring radius is about 3 milliarc seconds, although the contents of it usually evaluate to something a bit less than 1. So kind of half a milliarc second is about the typical size of the Einstein ring. And if you're familiar with telescopes observing from the ground or space, this is a size that we can't resolve. So we're not going to be able to resolve the Einstein ring for a stellar lensing event or resolve the two images. So we're going to have to observe this in some other way than kind of resolving those. I should put the caveat, if you use an interferometer, you might be able to do this in special cases. So what we're going to observe is this very close alignment of the two objects is not going to last very long. It doesn't take a star very long to move a milliarc second on the sky. And so we're going to observe it by watching the brightness of the lens or the background star change as it gets lensed by the foreground object. The time scale for this is going to be characterized by the angular Einstein radius divided by the proper motion of or the relative proper motion of the source and the lens. So how fast they're moving on the sky relative to each other. And so for a typical solar mass object, this is on the order of months. It's also worth pointing out the physical Einstein radius. So I've described the angular Einstein radius. If we apply the distance to the lens to that as well, we get about 3 astronomical units is the typical size of the Einstein radius, which is going to be important when we're thinking about planetary systems. So let's see if this video plays. Okay, so this is what we're going to be observing. Now we've got the time dimension in here. So on this side, we have the lens system. I was showing you the side-on view. Now we're looking at it face on, looking at the sorts in the lens on the sky. Here we have the lens in red, the sorts in blue. Sorry for the jumping. Over time, the apparent position of the sorts will move relative to the lens. And then we see that the two images that get produced by the lens move as the source moves. In addition to moving, they change size as well. So the outside image, the major image, gets bigger, but it also gets squeezed. And then the minor image starts off very small, but then as the source gets close to the lens, it becomes quite noticeably big. And then if you add up the area of those two images and divide by the original area of the source, that gives you the magnification of the microlensing event. So if you have the source very far from the lens, you have a magnification of 1. But then as the source approaches the lens, the magnification increases and can get very large. Here it's only getting up to a factor of 3. This is relatively small for microlensing. It can get up to factors of 1,000. So changing in brightness by many magnitudes. Okay, so there's a couple of points that I want to re-emphasize, so I put them with a few, I'll kind of slim them down a bit. It's not me in front of the screen. I slim them down a bit. The one important point to take away is that each of these kind of physical or observables of a microlensing event, the angular Einstein radius, the physical Einstein radius, and the time scale, all scale as a square root of the mass of the object. This makes it very useful for finding small objects because you are not fighting a linear degradation in the signal. You're actually it's just reducing by a factor of the square root. So you can get down to very low masses with microlensing. If we put in typical values for the time scale, which is going to set all how we observe these events, as I said, for kind of stellar masses, you get a microlensing time scale of about a month. I should say the duration is twice this time scale. It's the half event duration. For a Jupiter mass object, its time scale reduces to about a day, still quite manageable in terms of observing. And then for Earth masses, the time scale comes down to about an hour. So all of these timescales are actually relatively friendly to us astronomers. We can run surveys for years to catch lensing events by stellar mass objects, and the timescale of even Earth mass planets is not so short that we would struggle to observe it if we can make a camera big enough and run it quickly enough. But what we're looking for in terms of Earth masses, Jupiter masses, or solar masses is going to dictate the observation frequency we need to achieve when we go searching for microlensing. Okay, that's single lenses. On to more complicated lenses such as planetary microlensing. I'll start out with the simple picture. So we can imagine planetary microlensing in a perturbative sense. And so sorry for those artifacts on the images. When the image when the major image, the image outside the Einstein ring, passes by another massive object like a planet, that image will get perturbed, and usually it gets perturbed in a positive way. It gets bigger when it gets close to the planet. And so on the light curve, rather than having the symmetric light curve of a single lens, we now get an extra bump on top of it as well. A similar thing happens for, apologize, find my mouse again. Is it? Come on, there we go. Similar thing happens for a minor image perturbation. So this is the image inside the Einstein ring now. If we put the planet inside the Einstein ring, That's going to perturb the second image, the minor image. This image is smaller, so it is less bright. Again, apologies for the compression artifacts on the zoom. And so rather than the perturbation that occurs to the minor image could be either constructive or destructive. So in some cases, when you have a planet inside the Einstein ring, and it doesn't show up well on here, you get a dip rather than a bump in the light curve. So that's the kind of simple picture. If I'm going to be more mathematically rigorous, what's happening to the source is that when the source is passing relatively close to the planet, it is not necessarily the image that's being perturbed, but the source is passing through kind of imaginary structures in the gravitational lens called caustics. And these caustics are regions where you go from having, oh, is there a question? I will, and that might take me a long time to answer. So can you answer it, ask it again at the end, and I'll get into it. It's a question about the nature of caustics. It's going into more detail than I'd like to at the moment, but I'll answer it at the end. So yeah, the caustics are regions where you have where you go from having well, in the picture I showed, you had two images. When you add an extra lens, you will always add an image. This image usually lives quite close to the lens that you added. But at caustics, you can get the production of two extra images. And so when you produce those two extra images, you get a jump in brightness. And that can lead to interesting light curves that have a very rich set of features. Even if you're not directly crossing the caustics, nearby the caustics, you'll have regions of enhanced magnification, which will shape the light curve that you get. So I should caution, this isn't the caustic I'm showing here for this event, but this is the caustic system here. So when you have a source crossing a caustic, you will have a ramp up towards it, and then as it crosses the caustic, you get this big jump in magnification. It passes through the caustic, and then it has to exit, and you get a big sharp drop. So this can make planetary microlensing features very, very easy to detect. These are extremely strong signals of kind of magnitudes in size, and they happen very quickly as well. So this drop is about an hour it takes to drop by 1 magnitude. So these are very strong signals that you see in these microlensing events. And the strength of the signal is only very weakly dependent on the mass of the planet. It's more the thing that the mass of the planet affects is the size of the caustics. So your probability of it, encountering them. And so this diagram is showing that to some extent. So there are two important parameters in planetary microlensing, in addition to the parameters of a single lens. These are the mass ratio of the planet to the star. Here I've got log mass ratio going from -2, which is kind of brown dwarfy mass ratios, down to -6, which is kind of Earth mass ratios. And then the other important parameter is the projected separation of the planet relative to the Einstein radius. So in the video, you saw the images kind of traveling around the Einstein radius. So if you have a planet near the Einstein radius, it's going to give you a large caustic. But if the planet is far away from the Einstein radius, it will be a smaller caustic. And so this is showing the variation in size as you change projected separation and as you change mass ratio. The mass ratio range is huge here. It's 4 orders of magnitude. The range in projected separation is quite small. It's going from 0.7 to 1.3. And so this means that microlensing is most sensitive in a relatively narrow range of projected separations. And just to be clear, this projected separation is where the planet is on the sky relative to the star at the moment that you observe. Then you divide that kind of physical separation by the Einstein ring radius. And so we call that parameter S. So going back to the, going back to the perturbative approach, we can relatively easily read off rough parameters for the planet when we see one in a microlensing event. I'm showing work here, visualization work of my student Farzana Zarabi, showing a simulated microlensing event from Roman. And here you have the, sorry, wrong button. Here you have the underlying microlensing event and then a planetary signal here that's of short duration. And so if you measure the duration of the planetary signal relative to the duration of the event, take their ratio and then square it because we have this square root of mass, you can recover a good approximation for the mass ratio. Here it's about 0.1 days divided by by 16 days, and I can't do that in my head. But if you do it, it comes out about 10 to the minus 6, which is about right because this was an Earth mass planet going in with a mass ratio of 4 times 10 to the minus 6. You can also get an estimate of the projected separation as well, based on where the planetary signal is relative to the peak of the event. Another way of describing this is what the magnification was at the time of the planetary signal is telling you where the source was relative to the lens. I should say, I forgot to say, the magnification that an event reaches, a single lens event, does not depend on the mass. It only depends on the separation of the source and the lens. So as you go closer to the lens, the magnification increases. Okay, so we don't do this kind of visual inspection when we are trying to recover planetary parameters from the microlensing event, although we might use it for getting initial guesses. The actual process for getting 2 planet parameters from these complicated microlensing light curves involves fitting a model. The nice thing about microlensing is it's an analytic model. Sorry, no. Yes, it's an analytic model, but it requires numerical solution. So the model that you're solving is a fifth order polynomial, and then you also have to account for the finite size of the source, which requires numerical integration. But it's math. It's not an approximation. You are or not a. I'll backtrack. It's a numerical solution, but it can be calculated very accurately. Is the point that I'm trying to make. But the features that you get in the microlensing light curves are not necessarily well related to other than what I described, the exact features aren't really well related or well matched to the parameters. And so the typical process for finding those parameters is you will start with a grid search. Here I'm showing a goodness of fit parameter as a function of mass ratio and separation, projected separation in units of the Einstein ring. And then the blue is a bad fit, and then these red and yellow areas are areas of better fit. Because you can have a minor image perturbation or a major image perturbation, you'll often end up with viable solutions that are less than 1 and greater than 1 in terms of their projected separation, or greater and less than 1 in terms of log of the separation. So you would first perform that grid search. You also usually do a grid search over the angle of the trajectory of the source relative to the lens. And then once you found some good potential solutions, you then run full modeling downhill fitting with all of your parameters free. So if you do that lots of times, if you do a survey for microlensing events, find lots of microlensing events and find lots of planets, you can start to do exoplanet demographics. So the exoplanet demographic problem for microlensing is essentially the same as it is for the other techniques. You have some number of planets that you find, and you would like to know how many you would have found if every star had a planet. So it's basically this division, the number of detected divided by either the number of events that you observed times the probability of detection, or if you contract those two, the number of detected divided by the number you expected. And so we can do the same thing you do for transits. You saw and radial velocities. You saw plots like these yesterday, where you evaluate, would I have seen this planet with these parameters if I put it into my microlensing event? And so rather than looking like these plots that you get for transits, for microlensing, they're going to look like this. They're not kind of all weighted to one side. The sensitivity region is in the middle of the plot, around separation of projected separation of 1 in units of the Einstein radius, with a sensitivity region that narrows as you go to lower masses or mass ratios. The problem is, I would argue, a bit more complicated in evaluating these detection efficiencies than it is for transits, because the signals vary much more. You in a transit, you expect the drop to be relatively small, so you don't need to worry about the changes in photometric precision. But with microlensing, you can get very large signals, which could be significantly larger than your photometric precision, even in relatively rare occurrences. The other problem that you have to deal with, the range of impact parameters for the microlensing events, leads to a range of different peak magnifications, and those peak magnifications correspond to probing different parts of the planetary system. And so this is on your right here. We have plots of the sensitivity for individual events from a demographic study, and you can see that they vary quite significantly. Some have a single peak, others have 2 peaks. So you need to, it's not something you can approximate. You really need to do this event by event to get an accurate measure of your detection probability. But it is worth paying attention to the scale on this plot. This detection probability goes from 0 to 1. And for high masses, it can be very close to 1 over a wide range of parameters. So what's going into making these plots? Essentially, you start with your observed microlensing event, and then you try placing a planet of different mass ratio, different separation, and different angle relative to the source trajectory in your lensing system, and look at how the microlensing light curve varies with as those parameters vary. So here we're changing angle on the left and projected separation on the right. And you can see you get either very little signal or a huge signal, depending on where exactly the planet is. And so this requires care and kind of making sure that you're densely sampling the grid of possible parameters to get good detection efficiencies. But if you do that, you can do demographics. You can put those detection efficiencies, sum them up over all your events, divide by the number of planets you detect, and get to a demographic measurement, either the overall frequency of planets, or you can start to do it in terms of the planet parameters. Because this is microlensing, the parameters that we are measuring are Q, the mass ratio, and the projected separation. We usually do our demographics in those parameters. And so this is 2 examples that are the most recent. We had a study from 2016, Suzuki et al., which measured the mass ratio function of microlensing planets and found wrong button again. Found an increasing, or a negative power law, so low numbers of large planets increasing to high numbers of low mass planets, just like we see with other techniques in terms of radiates for transits and m sin I for radial velocities. This was a study done a decade ago now. It involved 23 planet detections. And even with that low number, you can do a decent job and fit a power law to its distribution. But with more detections, you can do better. And so this is a study that came out this year by Zhang et al., which improves the number of detected planets to approaching 100, I believe. And so now you get smaller error bars on your measurements. You get smaller bins as well. And there is this hint of some feature in the mass ratio distribution. If I was talking to students, I would caution them that this error bar is only about, or this point is only about 2 sigma away, and you have multiple data points here. So you probably shouldn't read too much into that deviation, but it is a good. Was it the microphone, or did you have a question? I thank you for reminding me. I wanted to talk about the surveys that we're doing it. So I'll get to that in a second. I'll just finish up the point here. So yeah, this feature is tantalizing, but it is not. It's by no means something that we can say definitely exists. But if we do see features in its mass function, that is an indication of possible physics in the planet formation or planet evolution process. And that's very exciting. So we want to keep improving these statistics, make these bins smaller again, make the error bar smaller, and see if this feature is real. So yeah, thank you for the reminder to talk about the surveys that did this work. So this is decades of work now. The three main microlensing surveys that have been doing these exoplanet surveys are OGLE in Chile, MOA in New Zealand, and then KMTNet, which is a network of 3 telescopes, 1 in Chile, 1 in South Africa, and 1 in Australia. And so this network of telescopes allows you to get continuous coverage around the globe to kind of catch these planetary features that last from hours to a day. And so you can't just observe them from one place, you have to observe through the night from multiple locations to fully characterize those features. Yes.
Yes, we don't have too much time, so please save the questions till the end. And there'll also be a coffee break after the second talk. Thank you.
Thank you. So yeah, I'm running quite behind, so I'll go quickly. So we've measured mass ratio and separation. We would like to measure masses. How much time do I have? I don't.
5 minutes to allot time for questions.
Okay. So we don't automatically get the mass of an exoplanet from microlensing, but there are ways that we can get it in special cases. And then there's another technique that we can use to get it in most cases. So in special cases, we can get it from features in the light curve. When a source passes across the caustic, that caustic is a very sharp feature in the magnification pattern, and it resolves the source into a finite amount of time for that crossing. We can use that finite source effect and the knowledge of the color and brightness of the source star to estimate the angular size of the source star, and then the ratio of the timescale of the event to the timescale of the caustic crossing allows you to set up this equation where you can get to the angular Einstein ring rather than just the timescale. So that removes the proper motion from the observable that we did have, the timescale. And then if you're lucky, you can also measure an effect called microlensing parallax. I definitely don't have time to go into the details of it, but by observing from a different location in the solar system, either a satellite in solar orbit or at L2, you get a slightly different perspective on the microlensing event. And then that scale, that distance between the two observers that you know, allows you to place a ruler on a projection of the Einstein ring onto the solar system. Or you can rely on the orbit of the Earth to provide you that scale as well, if the time scale of the event is long enough. Those two things, if you measure the angular Einstein radius going in one direction, that's a cone, and then the projected Einstein ring in the other direction, that's another cone. And that gives you a unique solution for the distance of the lens. And then if you know the distance, you can get to the mass as well. That only happens relatively rarely. Especially you either have to have a satellite observing these, which doesn't happen very often, and be able to observe it from Earth, or if the signal for the orbital parallax is very, very slight. So here's an example showing kind of a 1%, 2% residual on the many magnitude light curve variation that you have. So it's challenging, and you only get this in a fraction of events. The other way is to wait. So if you wait long enough, the source and the lens of the microlensing event will move apart due to their mutual proper motion. And if you wait long enough and observe with a high enough resolution, you can see them separated, assuming that the lens is a star and is emitting light. And so if you can do that, you can measure their separation. That gives you the relative proper motion. You can get the angular Einstein radius. And then you also get a measure of the brightness of the lens, which you can use as stellar physics to get an estimate of its luminosity through with an unknown distance. So you set up two mass distance relations, and then they will cross at some point and give you a unique solution. If both of those methods fail, you can still do some modeling to try and get at the masses of the events by putting in the parameters that you know into a model that kind of models the galaxy, and then seeing what plausible set of stars would give you those parameters. There's tools, public tools to do this, although I would caution that the galaxy models that we use aren't really good enough yet, and so I'm just advertising a project that I'm involved with to kind of build public tools that can allow galaxy modeling to be improved by anyone who wants to. Which leads me to something that you can learn from this. You can learn about where in the galaxy, or by understanding where in the galaxy the planets you find are. That can tell you about formation mechanisms, because there's correlations between position in the galaxy and the metallicity. And most of the planets that microlensing is going to find are going to be in the bulge. And so that's a stellar population with a different chemical history, chemical evolution history to the disk. And so that presents interesting opportunities. You can also detect free-floating planets with microlensing. Tell me if I need to stop. Okay.
So that we can leave a little time for questions.
Yeah, I will just finally advertise that this is not the end. This is just the beginning. Next year or the year after, the Nancy Grace Roman Space Telescope is going to launch. It's going to do a dedicated survey of the galactic bulge with the primary aim of detecting microlensing events, which should find thousands of exoplanets, which will do that thing that we need, which is increase the precision of the mass functions that we can gain. It will get down to lower masses. This is a simulated event of a Ganymede mass planet. And it will also, by doing this over 5 years and from space, it will measure the separations of the lenses and sources for most of its events and get masses too. So I'll stop there, and thank you.
Thank you. I'll start with an online question, since it's one that I'd like to ask too. Can TESS, so two parts, can TESS find microlensing events, or has TESS found microlensing events? And two, what in particular do we need to do? What do we need to worry about in addition to the promise of Roman? What are going to be the challenges for realizing this with Roman?
Okay, so yes, TETS can find microlensing events. It has found, I believe it's observed some kind of stellar microlensing events. I don't have numbers off the top of my head, and potentially a free-floating planet as well, although that is a little controversial. But the main problem for TETS is that most of its stars are very close, within a few hundred parsecs. There's not many other stars in between us and those stars that it can actually observe, so they're pretty rare. And then the question about what are the challenges for Roman. There's lots. Probably the biggest challenge is that there are not many people working on microlensing, and there are lots of problems to solve. So if you are interested, we are hosting a data challenge towards the end of the year. And we have a website set up for landing on it. It doesn't have the data challenge up yet, but it does have a set of tutorials that you can work on, a mini course that will go into more detail than I had time to on how to do microlensing. So if you're interested in getting involved, that is one way to do it. And then the data that Roman produces will all be public very quickly. So there will be no barriers to you actually using the data.
Yeah, this is Chaz. I'll point out that the next Sagan Summer Workshop, the topic is indeed microlensing and all of its gory glory.
Thank you. Let's start. Stuart, you were up, and then we'll go. Go ahead.
The current by semi-major axis, I realize it's probably a little difficult to translate. Are you able to go? Are you able to address the occurrence distribution by semi-major axis? I realize it's probably difficult translating from the separation.
Yeah, so this is a good question. So this plot shows the microlensing sensitivity as a function of semi-major axis. You can see that it's a lot wider than the distribution when you plot this in terms of projected separation. You can think of a projected separation or the Einstein ring as essentially sweeping across the system and just kind of lasering in on a particular system where it is. So for individual systems, you only get a narrow range, but when you sample the full range of distances to the lenses and masses of the host, you get a much broader spread in semi-major axis. But it's going to be a challenge to go from projected separation to semi-major axis. Getting the masses helps in this because it gets you to you also get the physical Einstein radius when you get it. You still have a projection effect, but it is an improvement on what you have without it.
Yeah, great talk, Matthew. Chris Lamb from University of Florida.
Speak up, please, so that people online.
Yeah.
Yeah.
Okay. Hi. My question is, we talked a little bit about the science difficulties, like the degeneracies from microlensing modeling. I was wondering if you could comment on like the technical difficulties associated with microlensing modeling. Like, I have no idea actually what's like a typical runtime, for example, for fitting like a planet.
Yeah, so it is certainly a numerical challenge. So if I can find a slide, no, I'm struggling. So I'll just answer the question. So yeah, computing the light curves, you need to do this numerically. It can be pretty slow to evaluate a single model, probably up to about a second. And then if you want to do fitting on that, you need thousands of these. And then if you're going to do Monte Carlo, Markov chain Monte Carlo error estimates, that gets you up to tens of thousands of evaluations that you need to do. And so that takes a long time, especially as you go to these surveys with larger and larger amounts of data. So it's a computational challenge, but it is one that you can mostly solve with brute force if you sample well enough. But I've only talked about the very simplest case, right? One planet and one star. Planetary systems can have multiple planets. You can have multiple like binary stars hosting planets, and you can have binary stars as the source as well. So there's a lot that vastly increases the parameter space you have to deal with, and vastly increases the computational time. And we do one planet, one star very well. We're getting better at kind of multi-planet systems, but there's still a lot of room for improvement on improving those modeling processes.
Thank you.
So do a quick one online, and then the quick one online. Any prospects for exomoons?
Yes, so that's another option that we have, right? If you can detect a moon mass planet, then potentially if that moon mass planet or moon mass object is next to a planet, then you have the prospect of finding it. It does get a little bit hard because when you have two masses that are too close to each other, they tend to just look like a single mass. And at least for the Galilean moons in the Jupiter system, that's probably the most promising real life example we have right now. Those would be too close to detect for a typical microlensing event. Although if the lens was in the right place in the galaxy, you might be in luck. But if moon systems can be bigger than the Galilean system with slightly more massive moons, then it becomes a very real possibility. And Matt, sorry, I'm forgetting how to pronounce your last name. Just put your hand up. Oh, shouldn't do that. Just put your hand up and wave. He's done a study of the possibility of detecting exomoons in Roman observations. So
Thank you. Please feel free to put it in the chat in response. Last question. Thank you.
Thank you. So thank you for great talk. I'm Jang Ho-bae from Seoul National University. So I wonder, is there some possibility of false positive in detection of the events?
Yeah, that's a great question. So the biggest worry for false positives is in the free floating planet cases because you have very short signals that can be mimicked by things like stellar flares, although stellar flares are typically asymmetric in time, whereas free floating planets will have a symmetric signal. The shape of the planetary microlensing signals can vary quite a lot, and you can get cases where you do get kind of a flare-like profile. So it's a possibility. But if your data quality is high enough, at least for bound planet microlensing, usually the forms of the microlensing light curve are very, very unique, and there's nothing really that can mimic them. But as we improve photometric precision with Roman, we're going to run into problems with stellar variability, and that's going to be a problem for parallax measurements, I think, more than false positives for planets.
Thank you. Let's thank Matthew again, and we'll move to the next topic.